But the answer to our future warming is ancient.
Answer to our future warming is ancient.
A paleobotany unlocks Earth's past climatic archives. But these fossilized leaves are more than just remains.
These fossilized leaves are more than just remains.
They are precise records of ancient atmospheric composition. Specifically, the stomata density on the leaf surface. A stomata are pores plants use for gas exchange. A higher density means higher historical carbon dioxide levels. And this relationship is robust, proven across epochs. But now that we understand this mechanism, let's explore its application. Scientists use this data to build past climate simulations. These simulations must be anchored by real-world evidence. And the leaf data provides the ground truth for calibration. We reconstruct environments from the late Cretaceous period onward. Imagine a world significantly warmer, with different CO2 concentrations. The models show how plants adapted to these pressures. But these ancient analogs inform how contemporary species might respond. We seek patterns of resilience and vulnerability in vegetation. The internal structure reveals transpiration rates, key climate variables. But advanced isotopic analysis adds layers of temperature certainty. But now that we understand the data inputs, let's examine integration. But paleobotany doesn't work in isolation. It requires collaboration. Geochemists provide the atmospheric context for our plants. Sedimentology helps date the plant material accurately. The integration creates robust, multi-proxy climate reconstructions. We look back millions of years to see future possibilities. Consider the Pliocene epochie a crucial warming analog. Fossil leaves confirm past sea level rise linked to warmth. An illustrated scientist points to a specific data anomaly in the past. But this anomaly, when modeled, predicts current warming trajectories. And now that we understand the predictive power, let's address limitations. Fossil preservation is inherently patchy across deep time. Not all ancient ecosystems leave equally readable signatures. The fragility of the specimens demands meticulous, slow handling. Model uncertainty arises from these gaps in the historical record. Furthermore, plant evolution changes the baseline interpretation. A modern leaf does not function identically to its ancestor. We must account for differing photosynthetic pathways through time. But this requires continuous peer review and refinement of methods. At the human element, intuition still guides the modeling choices. But the clarity gained vastly outweighs these inherent challenges. And now that we understand the limitations, let's look forward. The future involves leveraging machine learning on leaf morphology. The AI can identify patterns invisible to the human eye. Processing petabytes of ancient data becomes feasible now. This refined data refines our projections for the next century. And it helps us understand current plant adaptation limits precisely. We test modern crops against simulated ancient heat stress. The deep past teaches us about deep-time biological survival. And global datasets, built from leaves, offer a unified picture. Every fossilized leaf is a piece of the atmospheric puzzle. The ultimate goal is anticipating ecosystem collapse points accurately. Understanding ancient carbon cycles informs our mitigation strategies. The scientific journey relies on persistent, patient observation. The integration of historical ecology with contemporary modeling accelerates solutions. Every serration, every curve, holds a piece of the climate puzzle. On these proxy records anchor our projections to proven reality. The ancient river of time informs the modern stream of action. The paleobotanist becomes a crucial cartographer for the next century. We look to the wisdom held in the quiet history of flora. For the future of climate prediction, the leaves never lie.